All right, so I want to go through the notes real quick with you for sections 1 3. Dr. Taylor did the pre-video problems with you, the pre-section video. So you should have already filled in any problem on the notes that say video. He's already worked out with you. So I'm going to continue with the other ones and go through these so you guys can fill those out with me. Okay? All right, so we've already talked about, or Dr. Taylor talked about with you, what a limit was. Okay? And the very first rule of thumb is when you have a limit problem, you always try by plugging it in first. Every problem you want to do that with. Okay, so if you can plug in the number, the x value of the limit, then and you get an answer, then that is the limit of the problem. So for number 3, the limit as x approaches 3 of x squared. Well, if I plug 3 into that, I do get 9, so that's my answer. Those are the nice simple ones, but a lot of you forget to just check when we get into the harder ones. So always remember, first rule of thumb, plug in the number, see what you get. All right, number 4, the limit as x approaches 1 of 1 over x, so that would be 1 over 1. I get an answer, so there's my limit. Okay? All right. Next thing is looking at what happens when you get that indeterminate form. So still, rule of thumb is plug in your number. Okay, so if I look at number 7, I plug in 4, the limit as x approaches 4. When I plug 4 into this problem, I end up with 0 over 0. That tells you a lot, so that's why you want to do this. If you get 0 over 0, that's that indeterminate form. That tells you that you will get a numerical answer for your limit. There is an answer out there. Okay? But all that means is you've got a different way to work it. So there's lots of ways to do that. That's what we're going to be working on for the first few days. So the first way to try to find a limit is to use factoring. Okay? So when you do a limit problem, you must carry this limit notation through all of your steps until you get to the part where you're actually plugging in a number. All right, so I'm going to leave x minus 4 on the top. Can't do much with that. But the bottom factors x plus 4, x minus 4. Okay? So now I see that I have a common factor. I can cancel it out. So that ends up giving me, again, carrying through this limit, 1 in the top and x plus 4 in the bottom. Now I'm going to take this as my new limit problem, and I'm going to plug in my x value now. So that's 1 over 4 plus 4. I get 1/8, and that is my limit. Okay? All right, let's do one more, number 8. Again, if I put 3 in here, always check. 3 squared minus 3 times 3 over 3 squared minus 2 times 3 minus 3. That ends up giving me 9 minus 9 in the top. 9 minus 6, 3, minus 3, 0. So I get that indeterminate form again. So that means there is an answer out there. So the first method, factor. So in the top, I can factor out an x. And in the bottom, that factors x minus 3 and x plus 2, right? Factors of 3. Oop. It's a 1, not a 2. All right, x minus 3 times x plus 1. So factors of 3 that subtract to give you 2. So x minus 3, x plus 1. All right, so the x minus 3s are going to cancel out. So now you're left with the limit as x approaches 3 of x over x plus 1. So there's your new limit problem. Now you can try substituting in the 3 again. 3 over 3 plus 1. So 3/4 is your limit. Okay? All right, so those are just your basic limit problems, plugging it in and then factoring. We've got a lot of other methods we're going to use, but for now those are the basic ones that we're going to start with. Okay. Next, the other option that Dr. Taylor went through with you is using a table. Okay, so Dr. Taylor did the first problem with you. The limit as x approaches 0 of 1 minus cosine of x over x. We plugged in 0 and we ended up with 0 over 0. So again, that means you're going to get an answer. Okay, well, we can't factor that. There's not a whole lot we can do with trig functions. So one of the ways is to use your table. So remember what we're doing. We're trying to get as close to 0 as we can without actually using 0, because we can't use 0, because we get that. But if we get numbers really, really close to 0, then we can try to zoom in on that number that we're looking for. So he did this one, and on the left side, as he got closer and closer to 0, he got numbers closer to 0. And on the right-hand side, same thing. He plugged in numbers getting close to 0 from the right-hand side and got close to 0 as well. All right, so we're going to do the same thing with number 10. Okay, so let's make sure this is indeterminate form, because remember, we might get an answer. If you get an answer when you plug in your number, you're done. All right, so this is the limit as x approaches 0, sine of x over x. So I'm going to try plugging 0 into there. Sine of 0 is 0, so that is indeterminate, so that means I will get an answer somehow. Okay? All right, so what I want to do is go to my calculator, get to where you can see this. All right, and I'm going to plug in the sine of x over x. All right, and I'm going to go to my table. I'm going to clear out those guys. And by the way, if you forget how to do that, you want to go to table set and change your independent variable to ask so that you can actually put in the numbers. Okay? All right, so when you go to the table, if you have any numbers in there, just hit your delete key, delete, and delete all those numbers out so that you've got a fresh, clean board. All right, so I'm going to put in negative 0.1, negative 0.01, negative 0.001. All right, so I end up with 0.998, 0.9999, and 1. So it's pretty clear to see that as I get closer and closer to 0 from the left-hand side, these numbers are getting closer and closer to 1. Okay, so they're approaching 1. So now I need to check from the right-hand side. So I'm going to use these numbers now. So I'm just going to go up here and hit delete. All right, so 0.1, 0.01, 0.001. So as I get closer to 0 from the right-hand side, I get the same values. So again, I'm getting closer and closer and closer to 1. All right. So if these numbers are approaching the same value, then that is the limit of this function as x approaches 0. Even though at 0 I didn't get a number, that's telling me I'm getting really close to that. So that means that the limit as x approaches 0 of the sine of x over x is 1. Okay, so I did that by using the table method. I didn't factor. Obviously I can't do that with trig. So there's lots of ways to find limits, and that's what we're going to be looking at for, again, the next few class periods. All right, so that brings us to this theorem, which we're going to use quite frequently. Okay, that says the limit exists when the limit from the left equals the limit from the right. Okay, that is 100% has to be true all the time. So the limit as x approaches a of a function equals L, if and only if, that's what that little sign means, the limit as x approaches a from the left and the limit as x approaches a from the right both equal L. If that's not true, then this can't be true. Okay? All right. Now, there's a third way that you can find limits, and that's by looking at the graph. Sometimes that helps. It just depends on the number. If it's a nice whole round number and you can see it on your graph, then great. Otherwise, you probably are going to have to use the table. Okay? So if we look at that same problem we were just doing a minute ago in number 10, here it is again, and it says let's look at it by graphing it. Okay? So if I graph it, so I've already got it in here, I'm going to hit zoom 6. All right, I'm going to zoom in just a little bit. All right, so we are looking at the limit as x approaches 0. So at x equals 0, okay, I can kind of easily see that if I approach 0 from the left, the y value is getting close to 1. And if I approach 0 from the right, the y value is getting close to 1. That's exactly what that table showed us. But remember, right at 0, there's an error, right? That's 0 over 0. There is no value right there. But that doesn't matter. What matters is what you're getting close to. So we are approaching 1 from both sides of 0. So that is our answer 1. So you can look at the graph as well. All right? So if we look at 1 over x in the next problem, okay, and I graph that. All right. This is asking me what is the limit as x approaches 0 from the right. Okay, so here's 0. So as I approach 0 from the right, my y values are going to infinity. Okay, so if a limit goes to infinity right now, we're going to say it does not exist. Because right now for sections 1.3 and 1.4, your limit value must be a number. Okay, numbers. So infinity is not considered a number, so if it's infinity, you're going to use does not exist. After section 1.4, that's going to change, but so that you can get through your web work assignments, just keep in mind, if you have a limit in sections 1.3 or 1.4 that goes to infinity, then you're going to answer does not exist. Okay? All right. Now, we've got a couple other examples on here that we want to look at graphically. Okay, make sure you understand what a limit is doing. All right, so remember, function values are one thing, limits are a different thing. Sometimes they're the same, sometimes they're not. Okay, they both are y values, but they're a little bit different. All right, so if we look at this picture and we want to know what f of a is, that's the y value. What is the y value when x is a? So here's the ordered pair. Okay, so that would be the point AL. So the function value is L. The limit, on the other hand, is what is y getting close to when x is approaching a from both sides, left and right. So if I approach a from the left, the y value is getting close to L. If I approach a from the right, the y value will be approaching L. So the limit is also L. Okay, so that time they both happen to be the same. But if you look at this part of number 13, this is a hole right here. Okay, so at A there is no function value. So this does not exist. Okay? There is no point g of A. Gone. However, the limit as we get close to A from both sides, remember, if I'm approaching A from the left, my y value is getting close to L. And if I approach A from the right, my y value is getting close to L. Doesn't matter that L is not there. All that matters is both sides getting close to that y value. So that is L. So there's a case where one exists, one does not. Okay. All right. Next. Piecewise functions. Always going to see piecewise functions when you have limits. All right, so let's look at what this means. So we want to find the limit of this function as x approaches -4 from the left. Well, if you approach -4 from the left, so think about where -4 is. So if you're approaching from the left, those are numbers smaller than -4. Well, numbers smaller than -4 would fit into this category on the piecewise function. So that means we're going to plug -4 into here. Remember, first rule of thumb, plug it in. So 7 minus -4 is 11. Well, there's an answer. So that is it. Okay, always go back to plug it in. All right, the limit as x approaches -4 from the right, that would be numbers bigger than -4, which would fall into this category. So that means I'm going to plug -4 into there. Well, that's my answer. Okay, now, what is the limit as x approaches -4? Remember, the limit as x approaches -4 is only going to be true or exist if the limits from the left and the right are the same. They are not the same, So therefore, this does not exist. Okay, that's that theorem that we looked at on the previous page. All right, let's try 2. Okay, so here's 2. We're going to approach 2 from the left. Those are numbers smaller than 2, which would fall into this category. So we're going to plug in 2 into here. So that's just 2. Okay, the limit as x approaches 2 from the right, that's numbers bigger than 2. So we're going to use the bottom. We're going to plug 2 into here. So 2 minus 1 squared, that's 1 squared, we get 1. So again, the limit as x approaches 2 cannot exist if these two are not the same. Okay? So you always have to check left and right before you can answer that final question. Unless, again, you can just plug it in. All right, let's try a few more. Here's a new graph. All right, first off, function value. That's the y value at 2. Okay, so here's 2. That's not a function value, that's a whole. So here's the function value. Okay, so when x is 2, y would be 3. That's a function value. It's nothing to do with limits. All right, now we're going to look at as we approach 2 from the left. So that's this way. So as we approach 2, where's y going? So that would be up here. So y would be approaching 3. Okay, that y value. The limit as x approaches 2 from the right. So if we come in from this way, look at your graph. Where's the y value heading? The y value is heading to 1. Again, I don't care that that's a whole, because I'm not looking right at 2. I'm looking at as I get close to 2. All right, well, these guys aren't the same. So that means the limit as x approaches 2 can't exist. So there's your answer. All right, now let's look at 5. Okay, what is g of 5? Again, that's a whole. Here's the function value right there. So that's 1. 5, 1 is your ordered pair. Nothing to do with the limit. All right, let's look at 5 from the left. The limit as x approaches 5 from the left. So this side. So we're getting close to this y value of 2. The limit as x approaches 5 from the right. We're getting close to this y value 2. So both left and right sides are approaching the same y value. So that means that is the limit. So it does exist. Okay? All right. So hopefully that's making a little bit of sense to you as far as limits go. All right. Last thing is average velocity. We're going to talk more about this in section 2-3, I believe. But there's a problem on WebWorks, so that's kind of why we've done this with you. Okay? So let's just kind of go through. Those of you in physics or remember this from high school days, we know that velocity, instantaneous velocity at any given point in time, is the distance divided by the time. Okay, that's a formula that we all know for velocity. Average velocity, when you see that word average, typically that means you're looking for a slope. Okay? So notice that the average velocity is going to be the difference of the two distances divided by the difference of the two times. Well, that is a slope formula. Okay? Distance would be like y2 minus y1, and the time would be like x2 minus x1. So that's a slope formula. Okay? So if we are looking for an instantaneous velocity and we don't know the distance, okay, then we're going to take the average velocity formula and zero in on that point like we just did with limits. Okay, so take a look at this problem. A ball is thrown up straight into the air with an initial velocity of 55 feet per second. Its height in feet, t seconds is given by this formula. Okay, so y equals 75t minus 16t squared. All right. Find the average velocity for the period beginning when the time is 2 seconds and lasting for 0.1 seconds. So that means we're going from 2 seconds to 2.1 seconds. Okay, that's the interval, so these are your x values. Then we want to do the same thing going from 2 seconds to 2.01 seconds. Okay? And then we're going to do the same thing. We want to go from 2 seconds to 2.001 seconds. So notice what we're doing. This interval from 2 to 2.1 is not very big. Okay, it's a tenth away from one another. But then we're going just from 2 to 2.01. So now we're only 100th away from each other. And then we're 1,000th away. So we're kind of squeezing that gap. So that's a limit problem. So here's 2. So let's say this is 2.1. Okay, so we're going to find that velocity just using the slope formula. But then we're going to do 2.01. So that's going to be a little bit closer. So our interval is getting a little bit closer. And then we're going to do 2.001. So notice we are getting closer and closer to 2 from the right-hand side, right? We're approaching 2 from the right. We want to get really close to that. So the very last question, estimate, that's important, okay? What is the instantaneous velocity of the ball at 2 seconds? Well, if you're at 2 seconds, I can't do the slope formula because I don't have 2 times and 2 distances, but it will be the limit of what we're getting really close to when we approach 2. Okay, so this is not a hard problem. It's just using the slope over and over again. All right, so let's start with the first one. So if I'm going from 2 to 2.1, okay, then I need some ordered pairs. So I need 2 to what? And then 2.1. So I'm going to plug these values into here. Okay. All right, so I'm going to do, actually I'm going to just do this on the calculator. So I need y values. All right, so let me clear out that last problem. So I put it here. Can you see that? Okay. All right. So we're going to do 75x minus 16x squared. Now I'm going to go to my table and clear out those guys. All right, so I'm going to put in 2 and 2.1. All right, so I got 86 and 86.94. Okay, because remember, we're just doing slope, and that's just, I need the x and the y values. All right, so slope formula. Okay, so we're going to do y2, or actually distance 2, but for me that's y. I'm thinking of that. All right, so y2 minus y1. And then x2 minus x1. So just a regular slope. Okay, so that gives me 0.94 divided by 0.1. So that is 9.4. And these are feet per second. Okay? So there's the average velocity between 2 and 2.1 seconds. All right, so we're going to continue to do the same thing. So on number 2, we want to go from 2, we're still starting at 2 seconds, but this time we're only going to last 0.01 seconds. So again, I need my ordered pairs, so I already have that. So I need 2.01. So I'll put that back in my table. So that's 86.108. Okay, so now I'm going to do my slope formula again. y2 minus y1, which is 86, over x2 minus x1. Okay. All right, so that gives me 0.108 over 0.01. So that's 10.8 feet per second. All right, so I was at 9. Now I'm almost at 11. Okay, so as I get closer and closer to getting my velocity as close to 2 as I can, I'm getting closer to 11 now. All right, so now we're going to go to 0.001 seconds. So just from 2 seconds to 2.001 seconds. All right, so one more time. So I already have that ordered pair. All right, so I'm going to put 2.001 in here. That gives me 86.011. Okay. All right, so now I'm going to do the slope formula again. 86.011 minus 86, right? Y2 minus Y1 over X2 minus X1. All right, so that gives you 0.11 over 0.001. So that is exactly 11 feet per second. All right. So remember the table we did. Remember the table before was 0.9, 0.999, and then we got 1. So as we got close to that point, you know, what we're getting close to, that is the limit. Okay? So we can easily see that when we get closer to 2, we're getting closer to 11 feet per second. All right, so the last part says estimate. So I want you just to remember this, that instantaneous is the limit as x approaches 2, right, our time, of those average velocities. That's kind of what we're doing here. Doesn't say it, but that is what we're doing for instantaneous. Because I'll always have students that say, well, how can I find the velocity if I just have 2? Okay, because you can't do y2 minus y1. Well, you can't. That's why we just went through steps 1, 2, and 3 up here, because we can get really, really close to 2, and then that's our limit. Okay, so the instantaneous velocity when the ball is at 2 seconds is 11 feet per second. So there's really no work you have to do on that last part, and you do have a web work problem exactly like this one. So at the last piece where it says estimate, then you do not do any work. You should be looking at your answers for the first few problems and figuring out what you're getting close to. Okay? All right, so that finishes up section 1.3 for you guys. So please make sure you're filling in the notes.